From the last class, we talked about isotopes, and we did this example number 1 of 2 atoms having the same number of protons. If you have 2 atoms have 35 protons each, that means those atoms belong to the same element. Remember, protons identify the element that you are dealing with. And so if 2 atoms have 35 protons each, it means they belong to the same element, and you have to look up the periodic table and see what that element is. And so this first example that we did on Friday is one that allows us to talk about isotopes. You can see one atom has 44 neutrons in this example, and the other atom has 46 neutrons. So they have the same number of protons, same element, that means, and different numbers of neutrons. At the end of it all, we said you can define isotopes as atoms of the same element with different numbers of neutrons, as you see here. And because of these 2 different neutrons, this would give rise to different masses. So we said you can define isotopes as atoms of the same element with different masses. Okay, those 2 definitions are correct. So let's look at this other example. Please take a pen and paper with you and be sure to work through the question. I'll give you a minute to work through the question. And tell me if these are isotopes of each other. But what we are saying here is A, mass 127. We subtracted mass 127 from 75 from 127. And notice here, this is tellurium. And atom number B is iodine because of the different protons. And we have made a conclusion. Are these isotopes? No, they are not isotopes. Why? They have different numbers of protons. Again, protons give us the identity of that particular element, all right? And right here, we have gone through this. We have said at the core, at the nucleus, that's where you have protons and neutrons. So that brings us to this question here, which is going to summarize a lot of information, confusion about isotopes and the masses that you see on the periodic table. So let's deal with the first one, and I'm going to give you a minute to work through this, okay? So make sure you note, these are neutral isotopes, and you take the mass as given. So this question mark is asking you to tell what that element is, and then you fill the table. Okay, a minute for each one of us to do so. I will come to a weighted mass in a minute after I deal with isotopes. Isotopes will have different abundances, and a weighted mass is an average of the 2 isotopes. So when do we use a weighted isotope or weighted masses? All right. So if you're given isotopes, use the mass of that given isotope. In this case, you will not use the weighted mass. Okay. All right. So let's work through this this table here. All right, let's look at the first row. So atomic number for this element has atomic number, is another name for the number of protons. And this element is number 42. And so this is MO. So I identified it using the atomic number 42 there. And so the atomic number is 42. And then the mass number is 96. Remember, it is X, A, and Z here. This is mass number. And this is the atomic number. And this, we are dealing with an isotope. X is the element symbol. All right? And so number of protons is the same as atomic number, 42. And there is a catchword here, the neutral atoms. So in a neutral atoms, the number of protons is equal to the number of electrons. So this is going to be 42. And you have to calculate the number of neutrons. So atomic mass is equal to the number of protons plus the number of neutrons. So again, you subtract neutrons from each side, minus n, minus n. So mass minus neutrons is equal to the number of protons, minus p, because we know we want to find n. So this is mass equals, so minus p m minus p equals to, so that will cancel out. So now you see the number of neutrons is equal to mass number 96 minus 42. And so you see here, this is 54. Okay. Again, this is an isotope. Just use the mass that you are given. And now then, the second one, you have to fill the atomic symbol. So we know it is number 22. You have to have your periodic table with you. 22. That tells us it is TL because it's number 22. All right. And then this is TI. 22 is TI, not TL. TI. 22 is TI, titanium. And that is number 22. So you put 22 here, and now you want to find the mass and put it right here where I've put the question mark. Notice now we have to find the mass number. We can fill the number of protons. It's a neutral atom. Atomic number is equal to is another name for the number of protons, that's 22. It's a neutral atom, and therefore it will have the same number of electrons. Now, we are given number of neutrons is 26. And so mass number is equal to protons plus the neutrons. So we want to find the mass number. It's going to be 22 protons plus 26. And this gives us 48. So you come here and put 48. So, and then the mass number is 48. So we have completed this table, and maybe some of you have faced this. This is typically one of the questions that you have. You have to use the mass that you are given as given for the isotopes. All right. Now that I've mentioned on the specificity of being very specific on using the mass that you're given, I want to move forward and talk about the averaged or weighted masses that we see on the periodic table. And notice we have said it's two atoms, each with different masses. So we are going to talk about the relative abundance of one isotope over another. So I now want to move forward and talk about calculating these weighted masses. And I want to start with an example showing us here. I want to show you how to calculate the atomic mass that you see for chlorine. and then we'll get the idea. So usually when we talk about the weighted mass, and averaged mass, the weighted mass usually takes into account the relative abundance of each of the isotopes, okay? So let's use chlorine as an example. Chlorine has two isotopes. We call them chlorine 35 and chlorine 37. Here is the question. Chlorine 35 has an atomic mass of 34.97 AMU and with an abundance, notice it's 75.76%. Most of the time, you find chlorine 37 in existence. It exists much more, 75.76% of the time. That is the chlorine atom that you would see. That's the isotope. And then you have chlorine 37. See here, the way I'm saying it, chlorine 37, Cl37. It has an atomic mass of 36.97 with an abundance of 24.24. Okay? And so usually when you add these masses, they should be close to 100. In this case, they're not. So let's say these are the two isotopes. Use the atomic mass and the percent of each isotope to calculate the contribution of each isotope to the weighted average. How do we do it? So remember, we are using the percentage and we are using the mass. So what we do here is we use the mass, 34.97, times the abundance. It has a percentage. It is 75.76 over 100. So that is a fraction. Usually it goes from 0 to 100% or from 0 to 1. Okay, that is an abundance. So it's 34.97 times 75.76 over 100. So this is the mass that you get, 26.49 AMU. Then you have the other mass, 35.97. That is the other mass here, times 24.24 over 100. This is a fraction. And that's going to be equal to, notice here we have taken care of the significant figures. The first number has 4 significant figures. This, what we are given here, has 4 significant figures in this case. So the weighted mass is given to us to 4 significant figures. Our answer here, when you multiply the percent abundance and the mass, in the first one, chlorine 35, it gives us 26.49 AMU, plus 8.962 AMU. And you are adding them together, remember, by the rules for addition. You line them up here, and you see this is what you get. So again, if you look up this number on the periodic table, or if you look up the mass of chlorine on the periodic table, you're going to see that this is the mass that is tabulated. This is the mass that you would find. It is 35.45 mu. So the sum is what we call the weighted average, or this is the weighted mass of the atom, the weighted average or the atomic mass of chlorine, which is 35.45. Now, let's make matters clear. When it's telling you to use the isotope, that's isotopic mass, use isotopic mass. Now, from now on, we are going to use these weighted masses from the periodic table as given, unless you're given a problem like what we have here. And so, okay? So I want us to have more examples here in order to clarify this. So let's go to the next problem, and I would like you to work through this problem, and we bring it together and see if you have gotten the right the concept. All right? Naturally occurring antimony consists of 57.25%. That's antimony 121, which has a mass of 120.9038 AMU, and 42.74% of antimony 123, which has a mass of 122.9041. Calculate the atomic mass of antimony, okay? So I'm going to give you a minute here to work through the problem. Walk through the problem, then we can compare our answers. All right, so we have 57.25%. Notice here what we have, 57.25% is the same as, notice, is the same as 57.25 over 100. That's 0.5725. So make sure this percent is important when you make your calculations. Times 120.9038. Okay, I've taken the liberty here to go past to give us more decimal digits, all right? So this one here, which is 69.21, and I usually, depending on the significant figures, I will put a bar here, the guard digit. Then the other one is 42.74%, which is 42.74 over 100 times 122.9041. And so that is 52.5292. I've just given the liberty here myself so that I can see how far I should go. And notice here then, you add the two, this is going to be 121.7466. Now, I want to give you some advice here on these masses, these large masses. You usually, if we don't give many decimal points, but depending on what the problem, how the problem is given, you can pay attention to the significant figures, all right? But what you see here normally, if you look at your periodic table, a number of these elements are given to 2 digits past the decimal point. So I advise we can go 2 digits past the decimal point. So this is the answer here. If you got that, that's fine. 121.75 is also okay. So, all right. So let's do another example. I'm spending more time on this section so that we all understand how to do this. Here is another question. Naturally occurring indium consists of 4.28% indium 113 with a mass of 112.9043 mu and 95.72% indium 115 with a mass of 114.9041 mu. Calculate the atomic mass of indium. Okay? Again, I give each one of us a minute here to do the calculation. If you have a question, I know. Okay, let's work through the problem and check ourselves. You want to notice something. this one with a higher mass, if it has a higher percent abundance with this mass, if it's 95.72% of the time, this is what it exists with a mass of 114. So we suspect that our mass should be closer to this one, 114.9, because the indium-113 has a percent that is low for 4.28%. So again, let's see. Here is the catch. 4.28 is equal to 0.0428. So here is where the catch is. 0.0428. Notice again, this is 4.28%. All right. These are three significant figures if I was to go by percentage as given. So in that case, notice how far I should go. I should go up to that. And then the next one, it is if strict with significant figures. Significant figures. Significant figures. If I'm strict with significant figures, or if we are, then we should cut it off here. And then from there, 95.72 is 95.72% is equal to 95.72 over 100. That gives us 0.9572 times. Notice these are four significant figures. So this limits us to this one here. So in other words, they need to be up to that if we were to pay attention to the significant figures, okay? In other words, this is going to limit our accuracy here. And so you add them, this is what you get. So you are going to add them. In other words, 114.8 could be our answer with the correct significant figures. So what we get, look at your periodic table. Antimony, if you look at antimony, actually, no, if you look at, not antimony, if you look at indium, it's actually 114.8. This is from the periodic table. And therefore, you can see this is, we now know how to calculate the average weight. Now let's summarize what we have done so far. It's just multiplying the percent abundance with the mass of that isotope. And then you sum up those masses. But it's possible you can know the total mass, but you don't know the mass of one isotope. You have to do some arithmetic to find the missing mass of the isotope. Okay, let's do another one here. As I said, I'm spending more time here because this is an important concept. Before I want to bring up the other one where we need to find the mass of one isotope. Gallium has two naturally occurring isotopes, gallium-69 with a mass of 68.9256 AMU and a natural abundance of 60.11%. And gallium-71 with a mass of 70.9247 AMU and a natural abundance of 39.89. You notice one of the percentages is 60, the other one is 69. Calculate the atomic mass of gallium. All right. Again, please listen to what I said. I said if we pay attention to significant figures with what we are given, and this is what I said. I'll go back. I said if strict with significant figures, this is what we get. So remember, I just advised us to keep 2 significant figures past the decimal point. So that's my advice. But if in the problem it tells you to keep strict 2 significant figures, then pay attention to that phrasing. All right? So then, for gallium, we have the 2 masses here with their abundances. Calculate the atomic mass of gallium. Can we do this for a minute before I move forward to solve one of the other questions that is important? And yes, it's true, you just keep the guard digits until the very end, okay? So convert the percentage. So let's see. So I'm going through the question because of time. I want to get to the next question. So gallium 69. So you have with an abundance of 60.11 over 100, that is 0.611. The other fraction is gallium 71 with 39.89. That is the fraction that we get. And so we multiply those fractions, 0.6011 times 68.9256 AMU. And you notice there, you get this mass here. So as one of us say, Donald, that you can carry the digits to the very end, which is what it's supposed to be. And so here, notice you have 4 significant figures essentially there. And so you have 0.600 times 68.92 AMU, you get this number here. So you notice we have given the liberty there, but we know we need up to this point here. We have to see where all of them line up. And then you have the other one is 0.3989 times 7092478. So you get this one here, and you add them together. Notice it's 41.4321. You put the guard digit there. And then the other one is 28.2919. Again, the guard digit is there. And so once you add them, notice what you get is 769 until the very end. So that is the right thing to do. So let's go to another one. This is the one that I want to get to and see how we can calculate this one. Antimony, which has an atomic weight of 121.75, has 2 naturally occurring isotopes, antimony 121 and antimony 123. If a sample of antimony is 42.70, which has a mass of 122, what's the mass of antimony 121? Where do we start from here? What is the unknown here? Any response? So there are only two naturally occurring isotopes. If that is the case, what is our assumption? Any response? What is our assumption if there are only 2 naturally occurring isotopes and we have the percentage of one? Can we find the percentage of the other? And if so, how do we do it? So yes, you subtract from what? The percentage of the other. The 2 should add up to 100, and therefore we know the percentage of the other. So, which is correct, we know the percentage of the other. So you subtract 42.7%. Antimony, this is the sample of antimony 42. If a sample of antimony is 42.7%, antimony 123, So with a mass of 122.90. So this percentage here, 42.7, has a corresponding mass of 122.90. So the percentage of antimony 121 is going to be 100 minus 42.7. And then you have to set up some arithmetic. So let's see how we do this. So the abundance of antimony 121 is going to be 100 minus 42.7, and this gives us 57.30. And therefore, 57.30% is 0.5730. And then we let the mass of antimony 123, it's the one that we don't know. It's X. Let's call it X, all right? And so notice what you have then. The one with an abundance of 42, so this should be, let the mass of antimony 121, antimony 121 be X. Okay, and so the one with 42.7% is equal to 0.427 times 122.9. So you get the mass here is going to be 52.783. Then the antimony 121, we don't know its actual mass. So it's 57.30%, which is 0.5730 times X. And then when you multiply these two, you get 0.5730X. So it's like what we have done, but you're now adding them. If you add them, see what you get. It's 52.473 plus 0.573X. And that is equal to the total, the sum, the weighted average, which is 121.75. And then from here, we want to find X. So first, you will subtract 52.4783 from both sides. And so you get this number. Then what we get? So you're going to get, all right? And so what you get then is 0.5730X equals 69.271. And then you divide both sides with the number 5730 divided by 0.5730. And I think this is what you get. That's my calculation. You can check that. And so this is how to find X. In other words, it's just setting algebra. The other unknown becomes X, and then find what X is, okay? Finally, this brings us to something I want to end up with in today's class. So whenever you are given the mass of a given compound, and then, for example, if it's copper 1 sulfide, in this case, this is the mass. So now we are going to use the weighted mass from the periodic table. So let's look at this question. What is the percentage of sulfur in copper 1 sulfide? So you find what we call the molar mass. You add the masses of the elements in the compound. So we are given copper 1 sulfide, Cu2S. So the molar mass will be 2 times the mass of copper from the periodic table, which is 63.55 plus 1 sulfur, that's 1 times 32.07. So this is the molar mass, the total mass here. And the percent mass of one element, here we have only 2 elements. What's the percentage of sulfur? The percent of sulfur is going to be the mass of sulfur over the molar mass times 100%, which is going to be 32.07 over 159.17 times 100, which is going to be 20.15. Since there are 2 elements, if you find the percent of one, assuming you have done good calculation, then you subtract it from 100%, all right? Okay, and so that is, that brings us to the end of chapter 4. And those of you who have not finished chapter 4, you can do chapter 4. So what have we covered in chapter 4? We covered the atomic theory. We talked about Dalton's atomic theory. We critiqued it. And we also talked about the atoms. It brought us to the atoms. And we said atoms combine in simple whole number ratios. Now, we talked about the nuclear model of the atom. The atom is composed of protons and neutrons and electrons. And protons and neutrons make up most of the atom's mass and are grouped together in a dense nucleus. Electrons comprise most of the atom's volume, and protons and neutrons have similar masses. While electrons have a much smaller mass, we calculated was 1831 times smaller. We talked about the charges of each of these atoms, of these particles. The proton has a +1 charge, an electron has a -1 charge, a neutron has no charge. And when protons and electrons combine in an atom, their charges cancel out. So in a neutral and uncombined atom, we have neutral charge, all right? And many of the machines and computers we depend on are powered by electricity, all right? And so we talked about the periodic table, the atomic number, and the isotopes. That brings us to the end of today's class. Have a good day.